Hey folks, 954 is a classic initial rate problem where you're changing the concentrations of the reactants, or actually in this case it looks like it's a catalyst, to see what effect it has on the rate in order that you could write a rate law. So if I write a rate law, classic rate law, with the concentrations in brackets of each reactant, and the H plus. Let's see what we get when we do a little analysis here. We could do this by inspection. There is a way to do it with calculations, but I think they've picked some nice round numbers here to look at. So for example, let's take a look at equation trial 1 and trial 2, and notice that if we double the concentration of the bromine, nothing happens to the rate. That tells us that there's a 0th order dependence on bromine. Has no effect on the rate. If I compare experiment 1 and experiment 5, I have a roughly 1 1/3 increase in the concentration of, is this acetone? Looks like acetone. And I have about a 1 1/3 increase in the rate. So that tells me I've got first order dependence in the acetone. For the catalyst, for the H plus, again, I notice that it's not in the reactant slot of this reaction. They have it above the arrow. I want to compare experiment 1 and experiment 3. Here it looks like I double the concentration, and it looks like it's pretty close to double. If I double this would be 1.4. I'm going to say that this is about 2 times. That's close enough for me. Usually orders are integers, and so it certainly isn't going up 4 times, and it's certainly changing, so it's not 0 or 2. So I'm going to rewrite my rate law so that I reflect the first order dependence in the ketone and first order dependence in the protons. Often they ask us to find the rate constant, and it doesn't matter what experiment you choose. If I pick, let's say, experiment 5, 7.6 times 10 to the minus 5 units. Units of rate are always molarity per time. In this case, I think somewhere it said seconds. I'm going to guess that it's seconds, molarity per second. The rate constant is what I'm after. The concentration of the acetone is 0.40 molar. The concentration of the H plus is 0.050 molar. And so if I churn the numbers, I'm going to get a rate constant of 3.8 times 10 to the minus third, inverse molar, inverse second. That makes sense. And that's going to be my rate constant under these conditions. Remember that rate constants are true only for particular temperatures. I'm also asked to make a comment on the mechanism. Let me reproduce that mechanism here. We've got the ketone reacting with H3O plus, or the proton, in the first step to protonate the protonate that ketone. That doesn't quite look great to me, but they say that's a fast equilibrium. And that intermediate, this is the way they've drawn it, reacts with a water molecule in the slow step. So the proton's delivered to water to give H3O plus. So you can see the catalytic effect. It's introduced and then it's comes out as a product. And then we have a fast step at the end. It actually looks like I made a bit of a mistake here. The proton according to this, didn't come from, it turned that into an alcohol. The proton came from the methyl group. And then for our last step, which we're told is a fast step, this is where the bromine comes in. And this is a reason why the bromine is not part of the rate determining step. CH2Br happens fast, and then I have an HBr here. So there's the mechanism, and does this mechanism conform to the rate law that we found up above? The slow step, the rate law of the slow step, I'll just kind of put that there, is going to be, we'll call this K2 times the intermediate. We know we're going to have to get rid of that at some point, times the water. Get that? And if I, let's see, write an expression for the intermediate from the fast equilibrium, that's going to be K1 times H3O plus times the ketone. Writing this ketone so much is slowing me down. That's going to be equal to K minus 1 times the intermediate. It looks like I forgot one species up top. Yes, I have to have a water here. Forgot to write that earlier. You might have noticed that. And so if I'm isolating for the, if I isolate for the intermediate and make a substitution into here, I'm going to get K2 times K1 over K minus 1. I'm going to get a water over a water, so that disappears. And I'm going to get the ketone times the H3O plus. Essentially, again, re-expressing this in terms of these other components gives me a rate law that mimics the one that we got from the data.